Okay, so it's a great pleasure to have Yoosik Kim from Brandeis and CMSA, and Simon's collaboration is multiple person. And so we'll talk about disk potential of Quadrics. So please, Yoosik.
Okay, so thank you very much for the invitation. So today I'm going to talk about the disk potential functions of quadric hypersurfaces in the projective spaces. So this is going to be the outline of my talk today. So first I'm put my research in a mirror symmetric context. And then I will, to make sure that we are in the same page, so I'm going to review the disk potential functions. And I will construct a Lagrangian in a quadric hypersurface, and then I will compute the disk potential for them. And then also we will discuss like the further the direction of possible applications of it. So motivation actually comes from the mirror symmetry. I mean, probably you guys are already very familiar with it. So basically, the mirror symmetry is a duality relation between the symplectic geometry and then complex geometry. So originally, the mirror symmetry actually studies was studying the duality relation of the Calabi-Yau varieties. But we can actually upgrade. We can actually extend the story to the non-Calabi-Yau setting. So by replacing space by the Landau-Ginzburg mirror, Landau-Ginzburg model. So the mirror space together with the regular functions on it. So today we are interested in the Fano variety on the A model side. So I'm going to put the A model side as a Fano variety, and then the mirror side will be the Landau-Ginzburg model. And the more close the conjecture along the line is the SYG mirror symmetry. So basically it says that, okay, suppose that we have the Calabi-Yau manifold, and then in other methods, the part of conjecture is the existence of special Lagrangian fibration. And then by dualizing that fibration, one can produce the mirror space. And then by the rule, and then actually we can upgrade the story to the Fano or more general varieties. So by considering the certain complement of an anti-canonical divisor. So let's then complement. At the complement we are considering the Lagrangian fibration, and then by dualizing, and then we can obtain the mirror space, and then as a compensation for the removing the divisor, so we have to encode the removed data on the superpotential. So we should so this superpotential is defined by the Fukaya or Ohta. Actually is coming from the counting of the holomorphic disk bounded by the fibration and the heating the remove the anti-canonical divisors. Okay. So main interest of the talk today is this object. So basically we will be interested in this talk, this object in this talk. Let's start the review of the disk potential. So let's think about the symplectic manifold X omega. Then let's think about the Lagrangian torus in it. So to define a potential function, the most important ingredient is the disk counting, which is called open Gromov-Witten invariant. To define open Gromov-Witten invariant, I need a moduli space of the holomorphic disk. So basically, let's choose the omega comparable most complex structure on X. And then we'll think about the J holomorphic map from domain, the disk to the X, whose boundary lies in the Lagrangian, and then class, the representing class by the disk is beta. And then we'll actually think about the automorphism of the domain, reparameterization. So as long as as long as two maps are related by this reparameterization, we'll identify them. And then we'll actually do the stable map amplification. So that's going to be our M1 beta. And then this modular space actually usually naturally comes with evaluation. So here, one is that one stands for the number of the markings, boundary markings on the domain. So and then we can think about the evaluation map at the boundary marking points. Then that one actually gives us the map targeting into the L. And the dimension of the modular space will be determined by some topological data. So for instance, like the dimension of the L and some Maslov index, and then the automorphism group, and then number of the markings. So here you can just think it as like the open version of the term number. Okay? I mean, so if you have the holomorphic sphere, modular space of rational curves, or rational map, and then you need to consider the term number as an invariant. So that's the open analog of it. Okay. And to define open group invariant, I will assume the following. So our Lagrangian L should not bound any Maslov zero, non-constant Maslov zero holomorphic disk. So under this assumption, then I can define the counting invariant as follows. So I'm going to think about the degree of the evaluation map from the modular space to the L. So, and I mean, this invariant degree can be non-zero only when the Maslov index is 2, because if it's 2, then everything's cancelled out, and the dimension becomes like the matching up with the target. So now you can possibly have the non-zero degree. And also this assumption actually tells us that this guy is indeed a cycle. Okay? So we can actually define something non-trivial degree. So let me give the baby basic example. So let's think about the CP1, and then let's add on the Fubin study form on it. And then let's think about the equator. So this is my Lagrangian, and this is my ambient space. So as you can see, we have a pi2 relative homotopy group as rank 2. So this one actually generated by the disk hitting the east pole, and then it's the other one disk actually hitting the north pole. Okay? And the Maslov index is actually can be computed by the intersection of the east pole and the west pole. Okay? So in this case, to making a right dimension, one needs to think about the disk hitting this pole is exactly one. So there's no ambiguity of an additional moduli of it. So, and then as you can see, we have only one disk here. So the counting invariant for this disk is 1, and then the other one is here 1. Of course, I mean, we need to give the suitably choose a spin structure to orient the modular space, but let me just talk about that. So there is some good orientation of it. And now potential function actually governs the deformation of the flow theory. So for that purpose, I will actually introduce the deformation of the flow theory using the flat connection. So let's think about the trivial line bundle over the Lagrangian torus. Then let's choose the flat sister connection on it. And then I'm going to choose, then the fundamental group of the torus is rank n in this case. Then let's choose a basis for the pi1. So let's say theta 1 through theta n. And then for each base element, I can associate a coordinate for the flat connection. So let's think about the holonomy of this chosen group. Theta I, let's say this is zeta I. And then moduli of the flat sister connection, which would serve as a mirror complex chart this time, has a coordinate zeta I. And this flat connection actually deformed the Lagrangian flow theory. I mean, usually the case structure map of the A infinity algebra or infinity category, actually in this case, filtered by the homotopy groups. So this is MK beta. So it's a case structure map, actually, which coming from the beta class. Because in the here, K means that we have the K input. So we have K input, and then plus one additional marking point for the output. So we have a total k plus one boundary marking point. And this is kind of a typical configuration for the case structure map of a infinity algebra. But for the deformation, I will also consider the holonomy of the which comes from the boundary of this disk. So we actually choose the flat connection, that we have the boundary, and then multiply them. Then we can actually deform our case structure map in this way. Then now we can define the superpotential. So we have so superpotential actually comes from the M0 term, so obstruction term. So by definition of this one, we have this, right? As you mentioned, as we've just mentioned, I've just mentioned, so it's filtered by the homotopy class. And this is the very definition. And then also we actually turning on the deformation nabla, so the effect is multiplied by the holonomy. And so notice that M0 beta 1 actually coming from the evaluation map in this way. So notice that we have no input, so it only have one marking, and then we have a moduli space, and then we have and then the marking actually will generate like cycles chains in the Lagrangian. So this one is actually agrees with evaluation pushifold of the M1 beta. And we make at the very beginning, we make an assumption. There's no muscle of zero holonomy disk. It means that it does not have any boundary component, no boundary. So what we can have, what we have is the degree times fundamental cycle. Then the superpotential is the coefficient of the fundamental cycle. So that part will be our fundamental cycle, the superpotential. And then here is one more treatment. So we have a holonomy, and then we have like the mirror complex coordinate zi. So we can actually write down the partial beta in terms of the base we choose, and we can have a G-linear combination. And then using the G-linear combination, we can express holonomy part as a Laurent monomial of the GI variables. So that's the new variable. And then sum them up, the modulus 2, holonomy disk. This is the only possible the condition for the making the n beta possibly non-zero. So we get the potential function. We can define potential function in this way.
Sorry, one question.
Yeah.
Sure. So the output for M0 beta is what? Is a homology class, or what's the output?
You mean the output of this one?
Yes.
Yeah, or it depends on the model. So if, for instance, if you use like the round model, maybe this can have like the differential forms. So most like the geometrically intuitive one is like the simplicial model. So we actually have the fundamental cycle, the sum of the simplexes.
Okay.
So you can think that so we have the freedom of the moduli, and then we have a marking, and then they will curve our L, right? And then that one will define something in the Hn element, Hn element. Yeah. So that's what I mean by the L. So under this assumption, it's going to be multiple times of the fundamental cycle.
Okay, thanks.
Okay, so that's the definition of the superpotential we have. So let's look at the example of the calculation in the very basic example. So CP1, we have the equator. We've already computed the counting invariant by the picture. Okay, and then let's choose a basis for the fundamental angle of the L. So in this case, S1. Then I'm going to choose the basis for the pion as the boundary of blue disk, the boundary beta, and then we associate the coordinate, sister coordinate Z as a holonomy of this partial beta. Then potential function, it should consist of two terms because there are two Maslov tolerant disks. So m beta here, and then here. So I'm just write down the expression here, and this one is 1 and 1. So we have this one, and then because we take this one as basis, this one is just 1 times this one, so we get the z, and this one has a negative 1. Okay, so we have the one of the g terms here. So superpotential of the CP1 of the equator would be g plus 1 over g in this case. Okay, then let me address some difficulty of the computation of the disk potential. The first difficulty lies on the classification of the holomorphic disk. Of course, I mean, this one is so simple because the dimension is very low. But if you go to the higher dimension, like the classification of the holomorphic disk, is not usually easy job. Okay? And moreover, if our moduli space is, let's suppose our disk moduli space have the standing assumption that it does not bound any Maslov, non-trivial Maslov zero holomorphic disk. Even in this case, our moduli space may not be transversal. Then maybe sometimes we need to use like some virtual perturbation, abstract perturbation, to perturb our moduli space to make it transversal. Then it's very hard to guess how to compute the counting invariant directly from the definition. So these are the main difficulties of the computing disk potential. Now let me summary some the known result along the computation of the disk potential. The first one is the Cho and Bo, Chorian and Yongun. They actually compute the disk potential of the toric fiber in a toric Fano toric manifold. What they prove is that disk potential function actually agrees with Given-Horibaka potential. Given-Horibaka potential is already known previously. That they actually, what they prove is that like so discounting something potential coming from the discounting actually agrees with. So here is the example. We have the CP2, and actually this potential, what they prove is that Maslov tolerant big disk actually are in a one-to-one correspondence with the facet of the moment polytope or the toric divisor, component of the toric divisor. So in this case, they have three terms in the potential function. And then later, Fukaya, Ohta, Ono, and then Woodward, and Cho and Ohta, and many others actually construct a Lagrangian flow theory on a toric setup. And furthermore, they define a disk potential for arbitrary contactoring manifold, NOV. I mean, the here point is that, I mean, usually if you're turning on the perturbation, I mean, the counting invariant actually depend on the perturbation. What they prove is that as long as we actually perturb in a Tn equivalent sense, and we have like a well-defined disk potential and solve the potential function. And then also Chan, and then also their one key main observation is that so F2 is not a toric cases, it's semi-final cases. But in this case, some of the toric components may contain the Chan number zero holomorphic disk. So to do the right counting, to do the right mirror symmetry, and the potential function actually, I mean, the potential function, when you compute the potential function, and then one should actually consider the disk contribution as well. I mean, we have the Maslov 2 disk, and then Chan number 0 actually sum them up to be Maslov 2 contribution. So to do the right thing, I mean, so we need to consider that configuration as well. Okay. In general, if beyond the semi-final cases, so we do not know how to compute it in general. And then Chan and Lau and Leung and Chang actually they gives an algorithm how to compute same potential function for the semi-final toric case. So one other development is a word crossing formula. Then one can actually, if you don't have to focusing on the toric fiber in the toric manifold, one can actually perturb our Lagrangian fibration by smoothing the anti-canonical divisor. So for instance, it's a C2 example. you can smooth it instead of these two components. Then after pushing this corner, then this we have the muscle of zero holomorphic peak, actually muscle of zero holomorphic disk occurs. And then this one actually causes the discrepancy of the discounting. And then there are some coordinate change between, because this muscle of zero holomorphic disk, and then we have the two chambers, multiple chambers can occur. And then through the chambers, there are like the work-causing formula, so that the potential functions are related by a certain coordinate change. Then that coordinate change actually this already appears in the conservative and the solvent as well. But their one is like they think about the family perturbation of the almost complex structure. But the formula is quite similar to that. Okay. And also recently Pascal F. Tonkonen proved the work-causing formula using the Seidels observation. Seidels observation is the flow theoretical relation between two torus actually can give us the work-causing formula information. Also, there's like another development. Here's kind of natural approach, because once you understand like the Turing manifold, and then people try to attempt extend their knowledge to the toric degeneration. So actually, Nishino and Ohta actually studies the following situation. So let's think about the toric degeneration. So it means that when x equals 0, we have toric variety. Let's assume that our toric variety is irreducible. And then let's think about the case when we have the certain complete integral system in the generic fiber. And then let's say this one actually converges to the Turing moment map through the certain continuous map and densely different region. So this one actually can be constructed by the Luan's gradient Hamiltonian law. And then they put some assumption on it. So the family is the algebraic family, the flat family is going to be the Fano varieties. And then furthermore, at the central fiber has like a conifold singularity. So this is picture for the conifold singularity. So we have like S3 actually shrinking down to the toric degeneration. And then this singularity can be replaced by the S2. So this one is like the conifold model. Okay. But if our toric variety, that kind of singularity, then what they prove is that the disk potential actually agrees with given Holbach potential. It means that it resembles like the Fano toric cases. I mean, in other words, there is a one-to-one correspondence between the muscle of holomorphic disk and facet. And actually, they using this framework, they study the Galpan settlement system for the type A partial flag variety. So, for instance, FL123 case, they actually has a toric degeneration to the toric variety associated to it. And then, as you can see, we have the 6 facets of this polyton. And then there are actually 6 muscle of holomorphic disks. Therefore, our potential function consists of the 6 terms. So that's what the Nishino and Ohta will study. But what if our toric degeneration does not have this, does not satisfy this condition? So indeed, actually usually happens. For instance, let's think about the most standard toric degeneration of the other types of the partial flavor variety, B and D type, for instance, actually does not fit into their scheme. And then even for the type A partial flag variety, there can be multiple toric degenerations. So usually that toric degeneration actually corresponds to the string polyton or the Newton-Cook body with some good condition. If Newton-Cook body actually has some nice condition, then we can actually construct the toric degeneration. And then, so we have this one is like the partial flag variety. Then it has like it possibly have many like toric degeneration. Okay, but so maybe someone actually has like the star condition, but some of one, maybe other ones, some of one actually does not fit into their does not satisfy their assumption. So the goal of this talk today is to enhance our understanding beyond the star condition. So I think to explain the ideas, and then the easiest and then clear example is quadric hypersurface. So let me focusing on the quadric hypersurface, and then possibly in the future direction, and then I will discuss how to generalize it to the more general situation. So let's recall the quadric hypersurfaces. So any smooth quadric hypersurface, two quadric hypersurfaces are symplectic by the merger argument. I have a freedom to choose the equation. So I'm going to choose this equation for my quadric. And then there is this quadratic equation, actually one-to-one correspondence with symmetric bilinear form. So this one is the corresponding bilinear form. And the vanishing condition of this equation actually is the vanishing of the bilinear form. So because of this one, then quadric hypersurface can be viewed as orthogonal Grassmann. I mean, so the one is generated by this vector, this vector. And then this one it can be expressed as a homogeneous space, SON, and then quotient by some parabolic group. And then let's pass it to the real compact forms. Then we have the QN can be expressed as SON plus 2 homogeneous space. Okay. And then to construct a Lagrangian, I will realize our quadric hypersurface as a cogent orbit. So let's choose a G. Our G is here, SON plus 2. Then let's think about the cogent action. Then let's choose one element in the dual Lie algebra, and then acting on the cogent action, I can have the cogent orbit. It still is in the dual space. So let's make it more concrete. So I'm going to do the identification here. So by taking the Kelling form, and then we have the cogent action on the dual Lie algebra and adjoint action on the Lie algebra, then we can equivalently identify them. And then we can pass it everything to the Lie algebra side. And then this one is like n plus 2 times n plus 2 symmetric matrices in this case. And then cogent orbit actually correspond to the adjoint orbit and by the conjugate action. And then to realize our quadric hypersurface, I need to making a special choice for the element. Okay, so to define the quadric hypersurfaces, and almost everything is 0 except the 2-byte block, and the 2-byte block I'm going to choose this. Then you can easily see that SON plus 2 acts by the conjugation, and the isotopy subgroup looks like this. Therefore, this orbit actually can be viewed as quadric hypersurface. Then now I'm going to produce a Lagrangian vibration using the Galpan-Zettelin system. So let's choose to apply the themes tree. I'm going to think about the closed subgroups of the SON plus 2. So this is how the subgroup actually embedded into the bigger spaces. And our cogent orbit actually can be embedded into the n plus 2 by n plus 2 skew symmetric matrices. And then we have the projection and then projection, the projection. And then in the smaller, Lie algebra, actually there are conjugation action by SON plus 1 and then SON and so on. So by using the action, we can actually obtain a block diagonal matrix. And then through the block diagonal matrix, we can actually construct the Galpan-Zettelin system. So let's be more concrete. So here is a more concrete recipe to compute it. So if you choose the skew symmetric matrix A, and then let's say AJ is the leading J by J principal submatrix on it. And then to define these guys, I'm going to think about I will compute the eigenvalue of it. So recall that our O and lambda actually comes from the very orbit of the very special element. So eigenvalue cannot be arbitrary. So then submatrix eigenvalue must have this form. So one thing can be non-zero, and then the other must be 0. Okay. Then pi j actually gives by the coefficient of the pure imaginary part. So that's how the pi j defined. And then when SO2, then indeed there are two already exist. One is this one, and then the other one is this one. I need to distinguish them. I mean, this one actually gives the same eigenvalues, but they are in the different orbit. So then square root of the determinant, Papian actually does a job for us. Okay. So then by the work of the theme and Gilman and Stumber, they proved that this one is a completely integrable system. It's called the Gelpan-Zettel system. Now let's recall the peculiar property of the Gelpan-Zettel system. Actually, the image is a polyton, okay? And moreover, every fiber is a smooth isotropic submanifold, even over the critical value. Even if you choose a point, critical value of the movement, the fiber is smooth isotropic. And then by the joint work with Yoon-Young Cho and Young-Gun Oh, we describe the Gelpan-Zettel fiber in terms of leather dye and combinatorics. So we will recall that, but let me just state the fact from that the description. So in this case, the quadric hypersurface, and then this polyton image of the Gelpan-Zettel system is symplectic, which is given by this one. Okay. And then fiber over the interior of the polyton is a Lagrangian torus, just like the toric case. And the non-torus Lagrangian can only occur at the codimension 2 strata given by U2 equals 2. So here is the example. So let's say 3-dimensional quadric hypersurface Q3. And in this case, we have the simplex, 3-dimensional simplex, which looks like this. And then beside this codimension 2 strata, everything behaves like the toric. So if you choose a point, we have a torus fixed point, and we have here. And then we have the S1, and then 5 of the interior of the polyton, we have Lagrangian torus. And then something funny thing happened over this codimension 2 strata. Okay, so can have S3 or S2 times S1, both of them are Lagrangian, and then some S2 can occur over this strata. And then I actually talk about the one specific position of the fiber. So let's choose the very center of the polyton. So very center actually given by this way. So if you choose a lambda1 equals 10, so recall the lambda1 actually is ingredient for the cojoint orbit, and then we have this one is something to do with size of the polyton, because this one actually determines the symplectic one. So yeah, so depending on the lambda's size will varies. But if you choose an n, we can scale in there. We can always assume there's n, and then this position is the very center of the polyton, and then I'm going to focusing on the Lagrangian torus of it. And the reason that I focus on is as some geometric property, which is called the monoton. It's a monoton Lagrangian. So by definition, it means that the model of homomorphism and area homomorphism are positively proportional to each other. And then this condition actually ensures that we are in a good situation. So recall that, I mean, to define an open graph with an invariant, we have to make sure that our L does not bound any model of zero holonomic disk, non-trivial model of zero holonomic disk. And as you can see, if this model of index is 0, then this actually forces that symplectic area energy becomes 0. So it has only trivial disk can be actually the model of 0, which is bounded by L. And also furthermore, it's a monotone situation, like the counting invariant is actually really invariant under the choice of the generic choice of the most complex structure, because we can always construct cobordism between them. So that's the like the good property of the monotone Lagrangian. So then now let's talk about the potential function of the quadric. So setup is that we are thinking about the Gelpan-Zettel system. We are looking at the Lagrangian torus at the center, which is monotone. And then one more result from the Gilman and Sternberg says that so each individual pi I generate Hamiltonian collection on the dense subset. Of course, it's in general, quadric is not a toric variety, so it does not have the torus action, I mean, global Tn actions, right? But if you restrict ourselves to the open dense part, and then there is torus actions. And then let's say theta I is the orbit of the orbit generated by the pi I, and then collecting the theta I, which contains L, because L is constructed by the torus orbit. So we can choose as the loop generated by those actions. And then this is gonna be my basis for the first fundamental group of the L. And then I'm going to think about the mirror C star variable Zi, which coming from the holonomy of the theta I loop. Then theorem is that the superpotential can be expressed in this way. So to get a sense, let's look at the dimension 3 example. The superpotential actually consists of those terms. So recall that the Q3 is a symplectic. So we have 4 facets. So we have 1, 2, 3, 4 facets. So these 4 terms actually comes from the holomorphic disk, like they emanated from the inverse image of the facet. And one thing is that we actually have a very particular strata which have like Lagrangian SV, Lagrangian S times S1 S5, and S2 here. And then there are some holomorphic disks like the heating emanate from that particular strata. Okay, so that's the contribution of the red disk in this picture. Okay, then let me sketch the proof. The first one is that first ingredient for the proof is toric degeneration. So toric degeneration together with some topological argument actually gives some constraint on effective disk classes. So what I'm taking is the toric degeneration is this. I'm going to insert T here, and then we actually kill this guy when T is equal to 0. Then we have binomial. At the T equals 0, we have toric variety. And then this toric degeneration is compatible with the Gelpan-Setlin system and Gelpan-Setlin the polytor. The reason is that the toric variety associated to the lattice polytor actually looks like this. Okay? So this one looks exactly coincides with Gelpan-Setlin polytor. And moreover, actually, Nishino-Nohara actually proves that in this setting. So our Gelpan-Setlin polytor, which is coming from the eigenvalue, actually converges to the toric moment map over this polytor. Okay, so we have this the toric degeneration of the complex integral system. And our L was the fiber over the center, very center, which was monotone. And then our generic fiber, partial Clay variety, quadric hypersurface, minimal Chern number is greater than equal to 2. So something weird, something bubbling configuration cannot contribute to our potential function. So honest, this contribution can only contribute our disk potential. That's the good thing. And then one more observation is that if our class actually isn't effective, meaning that there are some holomorphic disks like the represent certain data class, and then let's say our disk actually hit. We already know that there are 4 disks like coming from the facet, and then let's ignore this part, and then there are some low dimensional the strata except the red one. So we have other one. If our pi actually hit this low dimensional strata, then the Maslov index should be greater than equal to 4. Okay? So the kind of main idea is that the X1, let's say, has a rank, this one actually has a relative homotopy group has a rank 4. And then X0 hat here means the toric resolution. So here, X0 is the toric orbifold. They have orbifold strata here. So let's cut it that orbifold strata. Then we can have the toric resolutions above. And then this one is the exceptional part. And then there are some sphere actually contract down. There are sphere actually can contract down to the point. Through the toric through the toric blow down. So this class, actually, if you like mod it up by that class, which is the Maslov 0 and Chern number 0, if you just mod it out, it's a rank matchup, and then you can actually construct, through this map, pi, and then this map, we can actually construct isomorphism between the homotopy group, a group isomorphism between the relative homotopy group X1 by the Lagrangian and the quotient group by the L. Then this one is Maslov index preserving, and then that actually topological argument will lead us that fact. So in sum, what we can do is that our potential function actually has something contributions of the facet, and then together with some contribution on this component, but we do not know the actual counting invariant or at this moment. But to determine the counting invariant, I collect some facts from the mirror symmetry and then Fukaya category. The first invariant is a theoretical mirror of Landau-Ginzburg mirror quadric hypersurface. And then Pech and Rietsch and Williams actually derive the Landau-Ginzburg mirror of the QN, which can compute the quantum cohomology ring. So in the mirror symmetry statement tells us that the critical value of the superpotential corresponds to the eigenvalue of the quantum cohomology ring. The C1 quantum coproduct actually acting on the quantum cohomology ring. And then using the eigenvalue, we can actually decompose our spaces. And then this value and the critical value actually correspond. And then here is a structure theorem of monotone Fukaya category by the Sheridan. One observation is before talking about the Sheridan's region. So let's think about the original form of the possible form of the potential function. And then this one has like the critical point. We can show that regardless of the value of the k, this guy has a critical point. That means that if there is some suitable C-star-like connection, which can make L is non-zero object in the monotone Fukaya category of the QN. Okay? And then Sheridan result says that actually this one actually has a summand of the Fukaya category of the lambda actually coming from the critical value, or equivalently coming from the eigenvalue of the quantum cohomology ring. And in this case, everything is one-dimensional somewhere. So indeed, this guy actually split generates some Fukaya category of some lambda. And using that information, we can actually give the constraint on the k, because already possible critical values are already predetermined. So the only possible k is limited. And then do some calculation. What you can prove is that when n equals 2, the only option is k equals 2. And n equals greater than 3, k is either 0 or 2. Then we have the one step more to go. And we need to determine the open graph invariant when n equals greater than equal to 3. So we actually have the following lemma. So to explain the lemma, let's look at this example. So this is Q3, this is Q2 example. Okay. We recall that pi 3 actually generates the Hamiltonian circle action of the dense part. So what I'm going to do is that I'm going to remove the inverse image of the two facets, and then pi 3 actually generates circle action on it. And then let's taking a reduction of C-star quotient of it. Then actually we can map down to the quadric hypersurface of dimension 2. And then we know that there are two holomorphic disks hitting this one by the previous calculation. And then actually we can lift it to the Q3 if we choose like the least locally product type complex structure. So of course, so we have the disk, and then together with some S1, and then we have the at least locally, we have a product complex, almost complex structure, then we can actually repeat it. But remember that we are playing with the monotone Lagrangian, so we have, as long as like if this is an invariant under the generic choice of the complex structure, we can perturb a bit, whatever we want. So then what we can have at the end is that, so M1 beta is actually has two components. And then there are, of course, so we need to give the orientation suitably coming from the Tn action. Then orient them suitably, then there is order preserving isomorphism between that. Therefore, this lemma actually tells us the counting invariant is 2. So one thing that we should note is that, so at the q equals 2, we have 2 different classes, but after the n equals 3, we have the same classes. The reason is after the compactification. Originally, we have the S2 vanishing cycle is here, but that S2 class becomes trivial after the compactification over the K3. So we have actually individual 2 different disconnected components. And then in sum, that's the kind of end of proof, and we actually achieved the PR. Now let's talk about the relation with other works. So that's the disk potential that we have just derived. And then sorry for the bad pronunciation, Przyjalkowski actually write down the Schur potential for studying the Qn quadric. And then potential looks like this. Then they actually agrees with some coordinate change. Indeed, I mean, the potential function actually embedded into the Pech, Rietsch, and Williams potential as a closed chart. I mean, if you choose some closed chart, the restricted to the PRW potential, and it's agreed with the disk potential. And so especially when n equals 2, and then secondary embedding actually gives us isomorphism between Quadrics and then CP1 times CP1. And this one was studied by the Oro and then Fukaya, Ohta, and many others. And yeah, of course, their Lagrangians different from the Gappan Z, maybe different from the Gappan Z-linear fiber, but they actually constructed their own Lagrangian, and then using the different method, and then they compute potential function that actually agrees with up to some coordinate change, agrees with this potential here up here, and then in the context of the Sheridan's homological mirror symmetry of the Fano hypersurfaces, of course, quadric hypersurfaces is one example of the Fano hypersurface. And then Fukaya category actually like decompose into these pieces where the lambda was eigenvalues of the C1 cup product. And then in this one, actually, indeed, you can have we can actually recover the full subcategory other than like the 0 critical value sum. Now, within the 10 minutes, let me talk about future direction and then future direction of it. Okay. So,
can I ask a question before you move on? So you said you don't pick up the 0 eigenvalue with this potential?
Right. So on a torus object can cover the non-zero eigenvalue component.
Okay, so for the 0, 1, you need to consider some other Lagrangian.
Exactly.
Do you know what that is or have a guess?
Okay, so Q3 and then Q4, I know how to do that, but beyond the Q5.
So we'll talk about that. Okay, so.
Okay, and of course, I mean Sheridan's immerse Lagrangian or Sheridan or Mikhailkin's Lagrangian actually correspond to the eigenvalue 0 summit.
Oh, okay.
But this one is like most torus and then like the singular torus kind of that approach. I mean, this but little different taste, but I mean his Lagrangian, I mean corresponds to that 0 summit.
Yes, sorry, just to ask based on that question. So what is a subscript lambda mean? What is a Fukaya sub lambda?
So we have the L lambda here. So we have the L nabla here. And then we have the potential function.
Yes.
And then when or lambda can be expressed as like the sum, the C star variable.
So you're taking the critical point corresponding to that lambda critical value?
Evaluate it and then we to the W and then it will give us some number critical value. So that's gonna be the lambda. Critical value, not the point.
Okay, so for this choice of this ZI, you still have this choice. You don't have to specialize those ZI to the critical point.
Special. Okay, I will think about every possible. I mean, okay. So, so structure of the monotone, the category looks like this. So we have L lambda, maybe different L1, L2, maybe different lambda. We have maybe possible many like objects in this category. And they have like their own potential for the L2, L3, L4. And then we have the critical value lambda 1, and we have lambda 2, and then lambda 3. So basically, the Lagrangians are interacting in the same critical value.
Okay,
so
okay.
They can interact only in that lambda slide.
I see. I see. Okay, okay. Thank you. Yeah.
Right. Okay. Then let's talk about the further direction. Okay. So we have the isotropy flag and then Johann differences that I want to also understand more general situation. So what I can say that is that is the quadric hypersurface and then T times 2 and then T times 1 model is going to be one of the building blocks for understanding isotropy flags variety. I mean, so by the classification of the Lagrangian fibers of the Johann differences and by the previous work that I did with the Cho and the Cho, and then cotangent bundle of the special orthogonal group, and then cotangent bundle of the SN, cotangent bundle of the somehow the real Steffen manifold is going to be the building blocks for that. So we actually understand the T styles too. Okay, so we actually embed it into the orthogonal Grassmannian, and then we do the critical value business to compute it. And then we have T styles 3. Then this guy actually can be embedded in certain orthogonal Grassmannian. In this case, this one is CP3. So then we know the structure of the Fukaya CP3 pretty well. So through that, we can actually determine the at least local potential function of it. Okay. And I believe that these are the two essential ingredients. Others at a higher SON and then a higher the Steffen manifold actually should we come from those. So namely, if you have like the isotropy flag, like a bunch of local models, so here we have the product of T styles 2 and the product of some SON and product of something, and then using the product, and then we can actually understand the local pieces and the local piece and the local piece, and then glue, and somehow we can combine the information together. We can. I expect. I want to understand it through that way. Okay. I mean, because essentially this is a final condition. I mean, there are not like the very weird configuration. I mean, multiple like the bubbling configuration of this structure. So I think that's the reasonable to expect. And also with Su-Cheng Lau and then Xiao Zheng, also we also working on the polygon spaces. That's the more immediate one, because by the work of the Bolo, the local model of the polygon space is given by the T styles 2 and then T styles 3 and their product. So this one is more, I mean, those two kind of blocks are already enough to understand the polygon space. Okay. And also, as I mentioned, I mean, so our torus object with a system flat connection actually can cover the non-zero critical value object. I mean, summand. So basically, one needs to fill up the critical value zero summand. So our kind of proposal is that instead of I mean, so partly because first of all, let me explain why this can happen. So because let's recall our polytype again. So we have Lagrangian torus. So this guy is monotone Lagrangian torus, and then we actually think about the sister connection add-on in, and then we actually think about the category of them generated by this one. But as we've mentioned, there are something interesting things going on this particular strata. So we have a bunch of Lagrangian, and then this one actually seems that this one actually contribute to like the other summand of the Fukaya category, like the lambda zero summand of it. So So this one actually kind of should in charge of that summand. And actually, the one approach is that, but I mean, this one is not a torus. So deformation space is like dimension of a deformation space less than the dimension of Lagrangian. So it's hard to make sense of the below. So previous work with Hansol and then Hansol Hong and Sucheng Rao, we actually use the immersed Lagrangian, immersed S2 Lagrangian, some torus, and then we actually smooth that corner, and then we did not talk about the Gaussian fiber. We actually construct a new Lagrangian coming from the left vibration like moda, and then we actually by gluing the deformation space of singular Lagrangian and then torus, actually we can obtain the partially compact mirror of the Q3 and Q4. But it will be interesting to investigate the higher QR. Yeah. So okay, so let me stop here. Okay, thank you for your attention.
Thank you. So I think people can ask questions now. Just unmute yourselves and go ahead.
Yeah, I have a kind of a general question. I'm always confused with this. This computation, it does not use the cell decomposition like Breuer decomposition of G mod P and so on. So is it really the case, or just my impression?
That's right. That's right. You're right. I mean, somehow the Pech and Rietsch and Williams, and then Rietsch and Williams, their collaborator actually used that scheme to construct the Lithia radical mirror. So they use like the decomposition. And each cell contribute like the one terms in the potential function. So yeah. So, but it seems like that once you're passing through the toric degeneration, I kind of lose the structure. Of course, one can directly construct a Lagrange. I mean, of course, I mean, their Pech and Rietsch and Williams mirror actually has their own anti-canonical divisor on the space, but there's no Lagrangian torus there. But it would be interesting to just directly look at their anti-canonical divisor in their setting, like usually given by the projective Rietsch and variety or something like that. And then you construct Lagrangian there, and then by classifying the disk directly, which hits their anti-canonical divisor, then one can probably expect that their potential is directly kind of recovered from that philosophy, but it's hard to make sense of it directly using constructing Lagrangian and then classifying the disk. So this kind of detour. So instead of looking at this one directly and then toric degeneration, and then you look at the local pieces, and then toric degeneration is more malleable to like classifying the disk and then computing something. That's the reason I kind of taking advantage of the toric. But of course, yeah, you're right. I mean, it would be very interesting to look at the direct picture of it. Yeah.
Mm-hmm. Okay, thank you.
Other questions?
Hi, I have actually a specific question.
Oh, yeah.
So the picture of this, first a more general question. How do one usually get this torus vibration? Suppose I just give you a flag variety or partial flag.
Oh,
how do you construct this?
Okay. So maybe let's look at this picture. So probably the one work then you can rely on is that if you are only interested in the toric Lagrangian torus and not the singular one, if you're just interested in the torus fiber, then the work is the Harada and Kabe, and all the Gelpan-Zetlin one. Of course, I mean Gelpan-Zetlin one and J-Twin. actually, I mean, I already explained the ideas. I mean, the construction of the Gapan-Zettel. So we
Mm-hmm.
actually think of successive change of the closed
Mm-hmm.
subgroup of the little,
Mm-hmm.
and then we actually think about the orbit, and then we
Mm-hmm.
collect them. Then we can construct a certain explicit complete integral system. So that works for the A, B, D type partial flavor, not
Okay.
for the other type.
Mm-hmm.
So that one has an advantage because that is so explicit. We can see what has happened at the boundary. Boundary, when we get the fiber, they are something like a small size groups of manifold, and we somehow explicitly say what they are.
Mm-hmm.
But okay, I don't care what has happened at the boundary.
Mm-hmm.
I want to tell off the Lagrangian torus vibration.
Mm-hmm.
And this one, you can apply the Harald-Cabes general work. So it means that they have the toric degeneration, which is coming from at the center, we have toric area over the certain open body, and then with a good condition. And that's also the irreducible, some other blah condition. Then we have the toric moment map associated with it. And then by pulling back the toric moment map, one can construct a completely integral system on the general fiber. The good thing is that in the dense part of the polytope, the fiber over this point is toric as a Lagrangian torus.
Sorry, so you have this toric generation first, and then you pull back that moment map. It's not directly you build from some complete integrable system.
Yeah, it does give a complete integral system.
Ah, okay.
It does. Yeah. So that's the main theorem, one of the main theorem of them.
Okay. Okay. Another question, maybe more specific, is like on page 11, you have on that red line and the purple dot. So what do you mean by over that red line? Is that fiber over each point is a S2 cross S1, or is that fiber over the entire interval?
Exactly. So you choose to pick a point in the one dimension, right? Fiber of the topology of the fiber is S times here.
S2 cross S1.
Point, S times another point, S times S.
Okay, so and you're saying on the corner somehow it becomes S3.
Right.
And how about on that other edge, that linking to the upper right point? On that edge, what's the fiber look like?
So except this red line and then purple and then green one. So
it's a usual story.
Is the usual line.
It's going to be the two torus over.
Here here this
so one
torus C2 and then S1.
I see.
S1 over here in the front page.
Okay. Okay, it's kind of hard to imagine how this vibration goes. All right, thanks.
Hi, so I'll ask maybe one more question. So you said that in this Q2 and Q3 case, right? You have these immersed Lagrangians, right? The other pieces that are missing in the category. But do you think or do you know if any of these fibers that you were just explaining give you like the generators of that part of Fukaya category, or that's kind of too naive?
Yeah, I've tried, but I do not have the clear answer for your question at this moment. Yeah.
So, but do those?
Because I mean, the constraint is that so I do not want to like the matching of the by just like the Morphian space by Morphian or generate. I want to do the like somehow the gluing the mirror functions and so on.
Yeah, I understand.
I need something Lagrangian, and then I need to figure out the relation between the torus object that we start with. So I actually
understand you're trying to glue these charts, right? But I was saying that if you just look at the level of the Fukaya category, right? Is there like an object that generates this extra piece? So, and like, do these guys have the right potential at least? Do they live over zero?
Yeah. Right. That's right. That's right. Yeah. So actually, we can recover with Rietsch and Williams and then Pech, Rietsch and Williams potential. it's I mean, the way to showing this is that, okay, so potential function up to some coordinate, actually glued one actually agrees with them. And then their one actually already covered the critical value 0 part. So therefore, our one already covered the critical value. So that's how the argument goes.
Okay, thank you.
Yeah.
Any other questions?
We didn't actually analyze closed open map directly. We didn't do that. Yeah. We actually just using matching of the nodes. Yeah.
Okay. Any other question?
Yeah, maybe I have last question. We had a talk of Tony Yu here kind of recently, and somehow he convinced at least me that if you want to make computations on the Floer side, it's you can sometimes do it in non-Archimedean setting instead of using this kind of like maybe toric degeneration. I don't know. Have you tried to use a kind of non-Archimedean methods?
Right, especially immersed Lagrangian. So there is convergence issue. I mean, so in this talk, I'm just focusing the monotone Lagrangian torus. I do not have any convergence issue on the mirror space. I'm just playing with convergence is guaranteed. I can have just C star by plugging some number into the Q, the parameter. But to do the immersed one, I mean, I need to use Novick-Ferring. So then what we can get is that non-Archimedean valued field, or like that, yeah, that mirror should appear to the full generality.
Yeah. Okay, thank you.
Okay, one last chance. If not, I think so. Let's thank you, Yoosik, for a very nice talk. And that's it for today.